A rocket stepping into the vacuum of space leaves everything behind, including the atmosphere it needs to burn its fuel. To survive the journey, it must carry its own air. That air comes in the form of liquid oxygen, a pale blue reactive oxidizer that must be maintained at a freezing 183 degrees Celsius. Since Robert Goddard's earliest liquid-fueled tests, liquid oxygen has served as the chemical partner to rocket fuel, providing the volatile combustion required to generate thrust. Escaping Earth's gravity well demands thousands of gallons of it. The massive Saturn V rockets of the Apollo era relied on this exact cryogenic chemistry just to reach orbit. Without a way to safely store this freezing fluid for the duration of a mission, traveling to the Moon, Mars, and the deep space beyond is physically impossible. Space is cold, but a spacecraft in the direct path of solar radiation absorbs a massive amount of thermal energy through its metallic skin. The ship itself compounds the problem. Onboard electronics, life support systems, and engines continuously radiate heat inward toward the payload bays. This creates a physical conflict. The liquid oxygen must remain near absolute zero while surrounded by a constant influx of heat. This cross-section diagram shows what happens when that thermal energy penetrates the storage tanks. It triggers a physical reaction known as boil-off. The liquid oxygen absorbs the ambient heat, begins to boil, and rapidly vaporizes into a gas. As the gas expands, the pressure inside the sealed container spikes toward structural failure. To prevent the tank from rupturing, the expanding gas must be venting out into the vacuum and permanently lost. A continuous bleed of propellant over a multi-month journey strips the spacecraft of the fuel it needs for landing and returning, leaving the crew stranded. Engineers combat this thermal bleed with physical interventions designed to isolate the storage tanks. The first line of defense is multi-layer insulation, a series of specialized sheets physically wrapped around the exterior of the tanks. These layers act as reflective shielding, bouncing incoming solar radiation back out into space and starving the heat transfer process before it breaches the hull. But insulation alone cannot preserve enough mass for a deep space trajectory. The rocket needs to hold more oxidizer within its strict internal volume. This thermal gauge illustrates subcooled liquid oxygen, drastically chilling the fluid below its boiling point. Oxygen molecules lose kinetic energy, slowing down and clustering tightly. This creates a denser fluid, allowing 15% more combustible mass to fit into the exact spatial footprint. Maximizing density and thermal stability through subcooling provides the physical margins required to guarantee enough thrust for maneuvers far from Earth. Passive physical defenses eventually reach their limits against the unpredictable thermal environments of deep space. Modern designs incorporate AI-controlled cryogenic systems that constantly analyze temperature variations and microfluctuations across the spacecraft's surface. This localized artificial intelligence evaluates the telemetry to predict thermal failures, engaging active cryocoolers before boil-off can initiate. The target metric is zero boil-off. By neutralizing heat entry with active cooling, the system eliminates the need for venting entirely. This integration transforms the fuel tank into an intelligent, self-regulating ecosystem. Managing liquid oxygen within a single ship is only a fraction of the engineering challenge. Deep space exploration requires an interplanetary supply chain. The architecture of tomorrow relies on orbital fuel depots, massive cryogenic gas stations anchored in low Earth orbit. Spacecraft can launch from Earth with nearly empty tanks to save weight, dock at these depots, and fill up on subcooled liquid oxygen while orbiting. Refueling outside the atmosphere removes the severe mass constraints that have grounded heavy payloads for decades. Hauling oxygen from Earth's surface eventually becomes mathematically inefficient. The long-term strategy requires producing the oxidizer directly on other celestial bodies. On the Moon, automated facilities will begin processing the regolith, chemically extracting the oxygen trapped within ancient lunar minerals. On Mars, atmospheric processing plants will pull carbon dioxide straight from the Martian air, stripping out the oxygen for local storage. Manufacturing liquid oxygen at the destination turns isolated one-way scouting missions into a continuous self-sustaining interplanetary highway. The thermodynamic instability of propellant, rather than the mechanical scale of the engine, dictated the reach of space exploration. Layered thermal shielding, the molecular density of subcooling, and autonomous AI oversight systematically block and neutralize the threat of heat. Preserving those thousands of gallons of pale blue liquid ensures that human crews have the thrust they made to maneuver safely in the void. Reaching orbit proved we could leave Earth. Mastering the extraction and storage of liquid oxygen ensures we stay.